hopefully everybody feels relatively comfortable right now with the power rule. Everybody's good with using the power rule, I hope?
Yes.
Yeah? Okay, cool. So the power rule is really great when you have, something simple like polynomial. But it's not always the rule that you need to use. And sometimes you might have things that are far more complicated functions than just something like, 5x squared minus 3x plus 1, right? And then you need to find the derivative of something complicated, like maybe something really irritating like, x squared minus 3x plus 5 times x to the fourth minus 8x cubed 7x minus 1, right? If we were to have some function like this, how would you think we should go about taking the derivative? Besides using this rule that I've written up here already. Because there is a way we could do it right now.
Using the power rule?
Yeah, we could use the power rule, but before we could use the power, we'd have to distribute all these terms out so that we'd have a nice little polynomial. I mean, it wouldn't be a nice little polynomial, but it'd be a polynomial, right? And that would be a lot of work and a lot of chance to make an error. So it's a lot easier if we have a rule that allows us to just find the derivative when we have one function being multiplied by another function. So that was the case there, right? We had one function being multiplied by another function. And so in order to take the derivative of that, we use what's called the product rule. And we're going to really quickly prove this rule called the product rule that allows us to do this. I've already put the rule up here. The rule is if you have one function, u, times another function, v, its derivative ought to be u times the derivative of v plus v times the derivative of u. Okay, so that's the rule. You're going to memorize that rule, but we're going to prove why it's true right now. And I'm just going to give you a little hint as to how we're going to do this. We're going to add or subtract, or add and subtract this term, u of x plus h v of x, into the numerator. And so what we've got here is the limit as h approaches 0 of the difference quotient of one function u times another function v, which would be u of x plus h v of x plus h minus u of x v of x all over h. Everybody agree that this is what the limit as h approaches 0 of the difference quotient should look like for a function u times another function v?
Yes.
Okay, cool. So what we're going to do then is, like I said, we're going to add this term u of x plus h v of x, and we're going to subtract that term in the numerator of this. And it's okay to do that, right? Because if I add the thing and then I subtract the thing, it's really like I've done absolutely nothing, right? Would you all agree with that?
Yes.
All right. So there's my plus u of x plus h v of x, and there's my minus u of x plus h v of x, all over h. Cool. So you're probably sitting there thinking, wow, this math teacher is an idiot. Why did he just add all this other crap in here, right? That's exactly what you're thinking. Well, there's a good reason for it. And the good reason for it is we're going to end up splitting this up into two different limits by grouping some of the terms in the numerator together. So probably two of the terms in the numerator together, and then grouping the other two together and doing two separate limits. So anybody have a guess as to which two sets of terms they want to group together from the numerator?
Those with an h and those without.
All right, those with an h and those without. So I've got one term that does not have any h's in it. So you want that one to be on its own, or is that what you're saying? Or you want, and then you want the other three to be together? Is that what you mean?
It was, but now that I think about it, it sounds longer than it should be.
Okay. Well, let's start with this first term. We're going to group two terms together and then two other terms together. So which one do we want to try grouping with this u of x plus h, v of x plus h to try to simplify this down?
The last term.
The last term. Okay. All right. Let's do that and see what happens. See if this works out for us. So we got the limit as h approaches 0 of u of x plus h, v of x plus h, minus u of x plus h, v of x, all over h. And then we would add to that, we group these two together, right? And just because I like to put addition first, we'll call this the limit as h approaches 0 of positive 1 u of x plus h, v of x, minus u of x, v of x, all over h. Everybody good with that? Yeah,
Yes.
no, maybe, yeah. Okay, cool. So, well, did that help us out at all? What can I do with this first limit?
Factor out the u of x plus h.
All right, they both have a u of x plus h in them, so I'm going to do this on the next page here. I can factor out the u of x plus h. I'm going to have a limit as h approaches 0 of u of x plus h times, I believe it was v of x plus h minus v of x, right? And this is all over h. Right, if I take the u of x plus h out, we got v of x plus h minus v of x, and it's all over h. And what about the other piece of it? Is there something we can factor out of this one?
The VFX.
V of x will factor out, right? So we can make this plus the limit as h approaches 0 of v of x times, looks like we got u of x plus h minus u of x there, all over h. And what good was this? Was this any good? I think it was.
We got back to the limits of the difference quotient with the
Yeah, so if we look right here, I ignore that u of x plus h, right? I've got the limit as h approaches 0 of the difference quotient for v. And here I've got the limit as h approaches 0 of the difference quotient of u. I just have an extra v of x in there. Well, what's happening between this u of x plus h and all this other crap that's in here? They're being multiplied, right? And the same with the v of x. And when I have two different things being multiplied together within a limit, I can write that as two different limits, can't I? Just being multiplied together. Everybody agree that we could turn that into that? Any issues with that or no?
nope.
Cool. And so what's the limit as h approaches 0 of u of x plus h? Well, that ought to just be u of x plus 0 or u of x. And this right here is the difference quotient with a limit as h approaches 0 for v of x. So that is the derivative of v with respect to x. And then over here, as h goes towards 0, v of x is just v of x. And this is the difference quotient with a limit as h approaches 0 in front of it for the function u of x, which ought to be the derivative of the function u. And this is our product rule. Okay. If we have u times v, one function times another, its derivative ought to be u dv plus v du. Good or no? Any questions on how we got there or any part of that or anything? No, everybody's good?
How did in the first and third term, where did the over h go?
This one and this one. So remember, these are being multiplied together, right? So it's this times this. And if I tried to put an h underneath this also, then I should have had I should have put it here. If I tried to put an h under this also, when I multiply these together, I get an h squared, right?
Oh, yeah, okay.
So the h just gets applied to one or the other. We could have applied it to this one, but it makes more sense to apply it to this one because that's what we need for the difference function. Does that make sense?
Yes, thank you.
Yep. Any other questions on that? All right, so let's see if we can apply this. And we got a pretty easy one here. X cubed plus 1 times x squared plus 3. So we're going to use the product rule, and this is going to be our function u, and this will be our function v. So if we want to find the derivative of u times v, we have to use that rule, which is the derivative ought to be u times the derivative of v. And what's the derivative of v?
X plus h squared plus 3x plus h minus 1.
Oh, no, too much work there. Let's just using the power rule. What's the derivative of v?
Oh, I looked at the wrong problem. 2x.
2x, great, all right. And then plus v times the derivative of u, which is
3x squared.
3x squared. Okay? And this is the derivative of that. And if we wanted to distribute this all out, we could. We'd get 2x to the fourth plus 2x plus 3x to the fourth plus 9x squared. Or 5x to the fourth plus 9x squared plus 2x. Now, real quickly, just to prove that we need this product rule, if we try to just go through here and take the derivative of this and the derivative of this and multiply them together, that'd be 3x squared times 2x, right? That would give us, 3 times 2 is 6. That'd give us 6x cubed, true? And that's clearly not the same as this. So either this way is right or this way is right, but it doesn't seem like this other way that we did just now should be right. We could distribute this all out, couldn't we? If we wanted to find it, f of x would equal what? If we distributed it all out. X to the fifth plus 3x cubed plus x squared plus 3. And what does the derivative equal if I take the derivative of this? It should be 5x to the fourth plus 9x squared plus 2x, which is exactly what we got over here, right? So if we distribute it out and take the derivative, we get the same thing as if we use the product rule. Everybody good with that?
Yes.
Okay. Now you're like, well, why do I have to use the product rule when I could just distribute it out? It's much easier. Well, yeah, for this one, yeah, it's easier to just distribute it out. But when I give you something like the one that I wrote down earlier, where there's like 8 different terms in each one, that's going to be a pain. Or especially when I give you something like, sine of x times x squared plus the inverse tangent of x, and say find the derivative of that. Well, that's not just going to turn into a nice polynomial if I distribute that out, right? We'll have to use the product rule. So everybody see why this rule is going to be important to us? Hopefully. All right.
Yes.
All right, let's do another one. So we'll call this u, and we'll call this v. And so the product rule tells us that the derivative ought to be what? What should our derivative be? The product rule says u times the derivative of v. What's the derivative of v?
2x plus 3.
Plus what?
X squared plus
V.
3x.
V, which is x squared plus 3x minus 1, times du, which is 3x squared. And again, if we wanted to, we could distribute all of this together and come up with one simple answer. So 2x to the fourth plus 3x cubed plus 4x plus 6 plus 3x to the fourth plus 9x cubed minus 3x squared. And if we combine the like terms, we get 5x to the fourth plus 12x cubed minus 3x squared plus 4x plus 6. I'm good with this answer. I would also be good with this answer. I'm fine with either of them. So you don't necessarily need to distribute it all out if you don't feel like it. It's just another chance to make a mistake. So it's fine to leave it in the form up above.
So for limits, you could always like plug it into Desmos and see if you were right, checking your answer that way. Is there a way to easily check your answer for a derivative?
I mean, the only way is to graph it and like try and write the equation of the tangent line and graph it to see if it's actually a tangent line. But no, other than that, there's not a good way, except that there are like tons of calculators online that will do derivatives for you. So,
All right.
I mean, other than that, there's no like easy algebraic way to just check to make sure you did it right. All right, so let's do one more here. We're going to do x to the 1/3 power times x squared minus 3x plus 2. And we're going to find all the values where f of x has a horizontal or a vertical tangent line. So we talked about horizontal tangent lines. We'll have to talk about vertical tangent lines in a second. First, let's find this derivative. So how are we going to find this derivative? It's one function times another function, right?
The product rule.
So the product rule, that's right. I don't know why the little bar doesn't show up very well on my screen. So if u is x to the 1/3 and v is x squared minus 3x plus 2, our derivative f prime ought to be u times the derivative of v, which is
2x minus 3.
2x minus 3 plus v times the derivative of u. What's the derivative of x to the 1/3?
1/3 x to the negative 2/3.
Exactly. 1/3 x to the negative 2/3. All right. So then it's asking us to find all the values at which f of x has a horizontal or a vertical tangent line. So the horizontal tangent line means we know that the derivative needs to equal what? For a horizontal tangent line, our derivative should equal
Zero.
Yeah, all right. What about a vertical tangent line?
Undefined.
Yeah, our derivative would need to be undefined, right? Because that's the slope of a vertical line, right? The slope of a vertical line is undefined. And so if I want the tangent line to be vertical, the thing that shows me the slope of the tangent line, the derivative ought to be undefined. So how are we going to figure out when this lovely little equation up here equals 0 that's going to be a little bit of a pain. And also, when is it undefined? What we need to do is we need to find a way to simplify this down so it is just multiplication and division with no addition in the middle, right? The addition is what makes it more difficult to figure out when it's equal to 0. Because if it was all multiplied or divided, we could use the zero product property, but since there's the plus sign, we can't. So how are we going to get rid of that plus sign?
Expand everything.
Okay, we could, so if we expand everything though, then we're going to have a bunch of pluses or minuses. And I want it to just be a bunch of terms like times each other or divided by each other. So that's going to be a lot easier to set this equal to 0, right? Than a bunch of pluses with like weird exponents. How can I turn it into something like that? How do we normally solve an equation if we want to know when it's equal to 0? Like if I had x squared plus 5x equals 0, what would you do?
Factor?
You factor out what? You factor out the smallest x that they all have in common. So you have x times x plus 5, right? True?
True.
Yeah, that's how you would do that. So let's do the same thing up here. Let's factor out the smallest power of x that they have in common. So what's the smallest power of x? Is it x to the 1/3? Is it x to the negative 2/3? Which is smaller, x to the 1/3 or x to the negative 2/3?
Negative 2/3.
All right, so let's factor out that smallest power. Let's factor out x to the negative 2/3. So what does that leave us with? If I take x to the negative 2/3 out of this, what does the x to the 1/3 become?
X to the negative 1/3.
No. Remember, the thing that's in here, x to some power, when I add the exponents, needs to equal x to the 1/3, right?
So just 1?
Yeah, so it should just be x to the first, right? X to the negative 2/3 times x would give me x to the 1/3. So if I take x to the negative 2/3 out of this whole first term, I should just be left with x times 2x minus 3. Because if I distribute that x to the negative 2/3 in here, right, that becomes x to the 1/3 times 2x minus 3. What's left from the second piece of it?
X to the 2/3 times x to the 2 2/3. And then the rest of the thing?
No, not sure where you got that from. If I take x to the negative 2/3 out of here, then that x to the negative 2/3 is just gone, right? And I have a 1/3 left. And I still have an x squared minus 3x plus 2. Nothing inside of that x squared minus 3x plus 2 should change. Because this x to the negative 2/3, when I bring it in, I just multiply it by this on the outside here, and then it can be distributed through here all the way if we wanted to, if we were trying to do that. But I just need this term times this term to be the same as this term. And having a 1/3 out in front of that should do that for me. Does that make sense to everybody or no? Didn't you guys like factor stuff like this in AM3 and pre-cal and all that? Anybody still out there? You guys like awake and alive? All right, everybody okay with that or no?
Yes.
All right. Okay, so let's rewrite this as best we can now. We've got x to the negative 2/3 times all of this junk in the middle. So what happens to x to the negative 2/3? It should drop to the denominator. And I could start distributing all this out if I wanted to. I'd have 2x squared minus 3x plus 1/3 x squared minus x plus 2/3 all over x to the 2/3 power. Good or no?
Yes.
All right. Now I have these 1/3 and these 2/3 in here. Those are kind of a pain. Would it be nice if I had a common denominator of 3 for everything up there and could drop the 3 into the denominator? I think that'd be good. So let's do that. That one's already got a 3. Good or no? What can I do with all these 3's now? They can just drop down here. So this becomes 6x squared plus x squared, that's 7x squared, minus 9x minus another 3x, so minus 12x plus 2, all over 3x to the 2/3 power. Good or no?
Yes.
Okay, so first off, when is this thing undefined? Because this is our derivative. When is our derivative undefined? If which part, the numerator or the denominator equals 0?
Denominator.
Denominator.
The denominator, right? So if 3x to the 2/3 equals 0, which tells us that x equals 0, right? And then the derivative equals 0.
When the numerator is 0.
So sorry, say that again.
When the numerator is 0.
Yeah, when the numerator is equal to 0. So f prime equals 0 if 7x squared minus 12x plus 2 equals 0. Which gives us what? Does that factor? Sorry, I'm sighing at my child over there who's wandering around looking for his kazoo instead of doing what he's supposed to be doing in his math class or his regular class, whatever class it is. So what is it? Does this factor or no? No, it doesn't. So x equals 12 plus or minus, using the quadratic formula, 144 minus 4 times 7 times 2. Yeah. And 144 minus 56 is what? That's 88. And we can take what out of 88? Just a 4, right? So this becomes 12 plus or minus 2 root 22 over 14. Or x equals 6 plus or minus root 22 over 7. Where we have horizontal tangent lines. Good or no?
Yeah.
All right. I'm not sure how good you all feel about that because you're awfully quiet today, but let's take a look at the graph of this function on Desmos. So our original function was what? X to the 1/3, right? Times, what do we have inside the parentheses on that?
X squared minus 3x plus 2.
X squared minus 3x plus 2. Okay, and so We said that at x equals 0, we had a vertical tangent line. Well, it sure looks like it, huh? Sure looks like that's gone pretty much vertical on us there, doesn't it?
Yes.
Yep. And here's our horizontal tangent lines at 0.187 and 1.527, which, what did we have? We had 6 plus the square root of 22, right? All divided by 7. Yeah, 1.527. That's this one, right? And a minus gives us this 0.187 value. And that's how we could get a general idea of what the graph of this very strange function looks like. It's a good looking function, isn't it? It's got some interesting stuff happening. Wow, you guys are so excited by that. That's good. All right. The next rule that we're going to learn is the quotient rule. Okay. Quotient rule is for finding a derivative of one function divided by another function. So if I have u divided by v and I try to write it out as a difference quotient, that would be u of x plus h over v of x plus h minus u of x over v of x all over h. Would you all agree with that?
Yes.
All right, so now we're going to have to figure out something to add and subtract in here eventually. But before we do that, maybe what's the best thing we try to do to simplify down these complex fractions?
Common denominator.
Common denominator. So the common denominator in our numerator there is going to be v of x plus h times v of x. So this is going to become a limit as h approaches 0 of u of x plus h v of x minus u of x v of x plus h all over v of x plus h v of x. Good or no?
Yes.
All right. So any thoughts on what we want to add and subtract into here? No ideas? All right, I'll tell you. We're going to add in a second here, once I get to the end of writing what we've already got. We're going to add in a plus u of x v of x, and we're going to subtract a u of x v of x. And that ought to not change the nature of this, right? Because we've added and subtracted the exact same thing. And this is all over h. I almost forgot to write that on this other one. All over h, right? Still all over h. When it's all over h, what can I do with that over h?
Multiply by reciprocal, so add it to the denominator.
Exactly. So I can just put this in as an h down here in both of these. That'll make things a little bit easier. So now we need to group two of these together to try and come up with some nice, easy things that will simplify down. So what do you want to group with this one?
The very last term.
The very last term, okay? We'll give that a shot. So this gives us a limit as h approaches 0 of u of x plus h v of x minus u of x v of x all over h times v of x plus h v of x. And then we've got, I'm going to put a minus between these. I'm going to say minus the limit as h approaches 0. That'll flip the signs of both of those. U of x, v of x plus h minus u of x, v of x all over h, v of x plus h, v of x. Good or no?
Good.
Yeah.
All right. What can I now do with the first one?
Factor out the v of x.
Factor out the v of x, and with the second one, I should be able to factor out a
U of x.
u of x. All right, so let's go through and do that. So this ought to give us a limit as h approaches 0. We're going to have a v of x. Right, that's what we decided. Take out the first one, have v of x. No, u
Yeah.
of x plus h. No, that's not even the right one. Where do we go? V of x, perfect. U of x plus h minus u of x. All over h, and then v of x plus h v of x minus, and then the other one, what are we taking out of it? I believe it was a u of x plus h.
Yeah.
Times v of x plus h minus v of x all over h times v of x plus h v of x.
I think we just factored a U of x.
Was it just a u of x? No, it was just a u of x. All right. Sorry about that. There. Okay, so now what can we do?
Separate the terms so that you get a limit of the difference quotient.
All right, so we should be able to get this limit of the difference quotient right here, and then times all of the rest of it. So this is the limit as h approaches 0 of v of x. And then we've got the limit as h approaches 0 of u of x plus h over, or sorry, minus u of x all over h. And let's see, this v of x plus h v of x is both in this term and in this term, right? Could I just put this all over a limit as h approaches 0 of v of x plus h times v of x? Everybody good with that?
Yeah.
All right, and now we're done. Doesn't look as simplified down as what I had at the beginning, but it is. What's the limit as h approaches 0 of v of x? Should just be
V of x.
v of x. What's the limit as h approaches 0 of u of x plus h minus u of x over h? That's the
Derivative of U of x.
derivative of u, exactly, du dx, minus the limit as h approaches 0 of u is u of x. And then this one is the derivative of v. And this is all over, if I plug in 0 for h, this becomes v of x times v of x, or v of x squared, and that is our quotient rule that you're going to want to need to know. You're going to need to have that memorized. You're going to be able to use that over and over and over and over and over again. Any questions on that? Wasn't that fun? All right, we're going to memorize that rule. Let's apply it to this function, x squared minus 1 over x squared plus 1. So here we have u over v. So the derivative f prime of x ought to be v. And what is the second part of the quotient rule? V times the
Derivative of u.
Derivative of u, which is 2x, minus u times the derivative of v, which is again 2x, all over v squared. And what does that simplify to? 2x cubed plus 2x, and then minus 2x cubed plus another 2x, all over x squared plus 1 squared, or 2x over x squared plus 1 squared. Good or no? That makes sense to everybody or no?
Wait, isn't it 4x over x squared plus 1 squared?
Yeah, I should probably add those twos together, huh? Addition is hard. The calculus part was easy. It's just that addition part that's difficult. 4x over x squared plus 1 squared.
So differentiate just means finding the derivative.
Correct. Oh, yeah. I should have said that. Differentiate just means find the derivative. Yep. Any questions on that process? Not too bad. Once you know the rule, maybe proving the rule is a pain, but once you know the rule, it's pretty easy to apply. Yeah. All right, let's do another one. This is a quotient of two functions. And so all we have to do is use the quotient rule. So the derivative f prime of x ought to be, somebody tell me what's the first term I should have.
Four x squared plus 5.
Okay, that's a v, right, the denominator, times the derivative of the numerator, which should be
6x minus 1.
minus, then what?
Three x squared minus x plus 2.
Right, u, exactly. And then last term in the numerator should be
8x.
8x, derivative of the denominator, all over our denominator squared. I'm good with this answer. You don't need to simplify the numerator. If you want to, you can, but I'm not going to bother to right now. This answer would be fine on the AP test, but you know, if it was multiple choice, they might have it distributed out. So, everybody good?
Yes.
All right. Next rule that we want to talk about is this rule called the reciprocal rule. And the reciprocal rule is just sort of a corollary here to the quotient rule, where the numerator of your division is just a constant or a 1. And so if we were to go through and use the quotient rule on 1 over g of x to take the derivative, we would get this. And let's show that that's true. How do we do the quotient rule with this? We do the denominator, right? Times the derivative of the numerator. What's the derivative of the numerator? What's the derivative of the numerator? It's the derivative of 1.
0, right?
0, yes. Minus the numerator times the derivative of the denominator. The derivative of g of x is just g prime of x all over g of x squared. And so we should see that g of x times 0 will cancel out, and we're just left with negative g prime over g squared. If this was 2 over g of x, we'd have negative 2g prime over g squared. If it was, 7 over g of x, you'd have negative 7g prime over g squared. So this rule is just like I said, it's just kind of a correlate the quotient rule when you have a constant in the numerator. So if you memorize this, that's great. It might make life a little bit easier here and there, but you can always go through and use the quotient rule if needed. So let's apply this rule once here real quick. What should we get? Should be f prime of x equals what? Negative
6x squared plus 5,
Yep. G prime, right, numerator over
the denominator squared.
the denominator squared. Easy?
Yeah.
All right, spectacular. All right, before we move on to any other rules, which doesn't look like we're quite going to have time for today. I was hoping we would get to a few of them. We're going to talk about a couple of other random little things. First is reasons why the derivative may not exist. And so there are 4 reasons why a derivative of a function may not exist at a certain point. And those 4 reasons are a corner, a cusp, a vertical tangent line, and a discontinuity. So the first one, a corner, is pretty straightforward. Corner shows up on absolute value functions. Okay. And the reason why the derivative doesn't exist at this point is we think about a derivative as a limit. What is the derivative coming from the left-hand side, or the limit as h approaches 0 of the difference quotient coming from the left? What's the slope of this tangent line, or the slope of this function?
-1.
-1. And what's the slope coming from the right?
+1.
+1. And if the limit as h approaches 0 of the difference quotient from the left is not equal to the limit as h approaches 0 of the difference quotient from the right, well, then that should tell us that that limit as h approaches 0 shouldn't exist at this exact point. And so absolute value of x, that kind of function at that corner, doesn't have a derivative. Okay. All right. These are cusps. Anytime you curve into a point, it's called a cusp. So what we've got here is a cusp. This is another place where the derivative does not exist. This is something like x to the 2/3 power will look like this. A vertical tangent line, right, occurs when the tangent line is vertical. We already talked about that one on a previous problem, right? Vertical tangent line. Derivative would be undefined there because, well, that sort of makes sense because the slope of the tangent line would be vertical. This is something like x to the 1/3 power. And then a discontinuity is the 4th reason why a derivative might not exist. And it wouldn't exist at a discontinuity because you can't have a tangent line if the function doesn't exist at the point. If there's a discontinuity there, if there's no continuity to the function, you can't draw a tangent line through that point, and therefore the derivative can't exist. Does that make sense?
Yeah.
All right, cool. We're going to be very concerned with when derivatives don't exist when we get into some of the basic applications of derivatives. Hopefully by the very end of next week, we'll have covered all the different ways to find derivatives. So We'll get into the basic applications hopefully at the end of next week. Good so far?
Yep.
All right. And since we have a second here, I don't really want to get into the next set of rules and derivatives that you're going to need to know. We're going to talk about how in physics, derivatives can help us with finding different functions. So if we are given a function that we call a position function, we'll call it S of t, the derivative of that position function should give us a velocity function. And the derivative of the velocity function should give us an acceleration function. And the derivative of the acceleration function should give us something called the jerk function. You all heard of the jerk function? It's not like your person sitting next to you in class that you don't like. But it's called the jerk function. It means a sudden change in acceleration. That's the derivative of acceleration. So each one of these is an instantaneous rate of change of the one above it, right? Velocity is the instantaneous rate of change of your position. While acceleration is the instantaneous rate of change of your velocity. It's how the velocity is changing. Jerk is the instantaneous rate of change of your acceleration, and so on. Anybody know what the derivative of the jerk function is? Nobody? Nobody knows what a sudden change in jerk is? How sad. It's called the jounce. What a great word, jounce. Guess what it's also called? Nobody? You can do this with your fingers.
Force.
It is snap. Derivative of jerk is jounce or snap. Anybody know the derivative of snap? I'll give you like 30 seconds to think about that. Derivative of snap. I'll be right back. Give me 1 second. Okay, sorry about that. I had to deal with something real quick. What's the derivative of snap? Anybody figure it out?
Crackle.
That's right.
Or pop.
No, the derivative of snap is crackle, but the derivative of crackle is
Pop.
pop. Like, no joke. Right? The derivative of jerk is snap, then crackle, then pop. Anybody know what the derivative of pop is?
Bang.
No,
Lock.
that's right. You know what the derivative of lock is?
Drop.
That's right. Anybody know what the derivative of drop is? Any like tennis players out there? Nobody? Nobody tennis? Maybe badminton? I don't know if they do that in badminton. Drop shot, right? You've heard of a drop shot, right? No? Maybe? Yes, no? Yeah.
Yes.
Derivative of drop is shot. What's the derivative of shot? Think track and field.
Put.
Put.
That was a straight guess.
Hey, you're right. So it goes position, velocity, acceleration, jerk, jounce, which is also snap, and then so snap, crackle, pop, lock, drop, shot, put. Those are all your derivatives. You don't need to know any of those except the ones that I already had written here. But I thought that'd be fun. Haha. Snap, crackle, pop. Everybody always thinks those ones are kind of weird. But that's actually what they're all called. We will talk a little bit more about these and how to deal with them on Monday. We're going to do a couple problems with them on Monday. And then we'll get into finding derivatives of trig functions and a bunch of other important rules that we need also on Monday. Sound good?
Sounds amazing.
Awesome.